the remote attack surface in Telegram, and specifically the animated stickers feature. This is going to be our agenda. So first, as always, a little introduction about who I am and what is the Lottie animation format. Then we'll have a look at the R-Lottie project developed by Samsung and its integration in Telegram. After that, we are going to have a look at the fuzzing efforts and my methodology I have used in my research. Then we'll analyze my findings, the issues I have identified, have a live demo of the issue, and consider some exploit limitations of my specific attack vector. In the end, we will have some closing remarks and a little time for question and answer. So let's jump right into the introduction. So I'm Paolo. I'm a vulnerability researcher and exploit developer. Currently, I am the research team director at Shielder, a cybersecurity company in Italy. In my free time, I enjoy backpacking around the world, and you can find me on Twitter at @polict_. So if you have any question after my talk, we can either discuss face-to-face or you can just DM me since my DMs are open. So what is the Lottie animation format? Basically, it was created by Airbnb, by their design team, and the core pro of using Lottie instead of PNGs or GIFs is that they are really smaller than the others, and after that they can also be manipulated at runtime. So it's really a nice pro over the counterparts. As you can see in this example, the Lottie animation was almost 5 times smaller than, for example, GIFs or even animated PNGs. Lottie animations are defined as a JSON file, so instead of having like a binary blob, there is a simple JSON file which will come handy afterwards when we will see structure over fuzzing. So who is using Lottie animations? On the right part of the screen, you can see an example of a Lottie animation. You might have seen this in Telegram itself, and since it's part of the animated sticker pack developed by Telegram. While on the left part, you can see some of the vendors or products that actually use Lottie animations. So here, most probably, the most interesting one is Signal, but we need to consider here that most of the other vendors besides Telegram actually parse and render Lottie animation coming from the file system and not from third parties. You can see also other examples like the Galaxy Watch, because as we will see, Samsung developed C++ library in order to parse and render Lottie animations called R-Lottie. While we'll have a look, a specific look at the C++ version, most of the other vendors actually use the Java or Swift library developed by Airbnb themselves. I will focus on the Samsung one since it is the one used in Telegram, but of course, another potential work for the future would be checking if those other libraries had similar issues. So let's have a look at the barebone example of Lottie animation. As you can see, as I mentioned earlier, they are defined as a JSON. So there is the outermost layer, which will include these 5 main keys, which, as you can see in the comments, are the version identifier, the frame rate, the in point, the out point, and actually the most interesting one from the point of view of the animation, which is the layers one. So let's move to the Samsung R-Lottie project, because this is the Lottie library which is actually used in all of the official clients of Telegram. As I mentioned earlier, rLottie is a C++ library developed by Samsung for parsing and rendering Lottie animations. It is open source and its code is available on github.com, so you can easily surf or instrument it. And the main advantage from what I understood doing this research against the Java or Swift counterparts is performance, because since it's in C++, the animations are parsed and rendered in way less time. An important thing to consider about rLottie is its threat model, since they don't currently track issues stemming from parsing and rendering untrusted images, as in third-party images or animations. This, of course, is a legit decision, but in the specific Telegram case, since they have a different threat model, since animated stickers are basically Lottie animations, so you can send a custom Lottie animation to another user, so it's not really the same threat model, since you can pretty much create an animation from scratch and send it to the other client, and the other client will try to parse it and render it. So it creates a problem from Telegram, since they will need to track and fix each and every issue they find, since the threat model is different. So let's have a quick look about how we can basically use rLottie, since as I mentioned earlier, it's open source, so you can directly use it and analyze it. Basically, it is divided in two main APIs, which are named like in a human way and are pretty easy to use. So the first is load from file, which will load in memory and parse an animation coming from the file system. And there is also load from data, which is basically the same one, but it actually imports it from a string object. While when we move to the render part, there is pretty much one single API, which is the render sync method, which will render the animation basically on a bitmap, for example, on the Android case that we will see later. As you can see in the render sync method, there is the frame number argument, which defines the specific frame we want to render on the bitmap. So, as we have seen, it's really easy to use it, and there are not much calls we need to do. So, our harness, which is the piece of code which we need in order to interface the fuzzer to the target API, is pretty much ready. So, we can just fuzz it. Before we move to the fuzzing part, let's have a look at the actual rLottie integration in the Telegram code. You can see here a little overview of the process. So once an animated sticker is sent, it is saved in Telegram's cloud and its coordinates sent to the recipient. This is because since you are sending a custom animated sticker, Telegram doesn't have it yet in their cloud, so they have to save it and send the coordinates to the recipient. In case you send an animated sticker coming from a sticker pack, it is already on the Telegram cloud, so only the coordinates, the cloud coordinates, will be sent to the recipient, so the recipient client. Once the recipient opens the chat, which is the case for the Android app, it is parsed and rendered. As you can see, there is a catch here, since some clients might actually parse and render the animation before you actually open the chat. So this makes the attack vector either 0 or 1 click, since you might need the user interaction of opening the chat. But this, as I said, actually depends on the victim's client. Last, as I mentioned earlier, the rLottie library in all of the official clients of Telegram is used in order to parse and render the animated stickers in the chat view. Since the Telegram APIs are really simple and easy to use, you don't even need an attacker physical device. You just need a computer in order to interface with the Telegram APIs and send the malicious animated stickers to anybody you want. Also, last but not least, by default, during my research, new chat from strangers do not have any additional protection enabled. So for example, secret chat from strangers do not have animations disabled by default. So you can just send a malicious animated sticker to somebody who has not you in their contacts, and the animation sticker will be parsed and rendered like it's normal. Let's have a look at the specific integration of Arlotti in Telegram for Android. As we can see in the above images, they come from the image loader file, which is part of the chat code base. As you can see, first the MIME type of the document which was received is checked to be the specific of the animated sticker. So it must be application/x-tg sticker. And as you can see, it will set the image type to image type Lotti, since it's a animated sticker, so it's a Lotti animation. After that, the Arlotti drawable object will be created, which, as you can see, will pass the local file system path of the downloaded animated sticker, the width, the height, and some other option that we don't care about. And in the end, it will finish in the load from file API that we have seen earlier in the Arlotti project homepage. And from there, there is going to be just the render sync method function call that will actually render the animation on a bitmap. So as we have seen, Arlotti is reachable remotely. There is no sandbox or specific protection or anything like that. Moreover, during my test, I noticed that I couldn't actually send malicious animated stickers in the clear text chat of Telegram, which is the default one, which is not end-to-end encrypted. So my guess was that Telegram is actually filtering bad stickers from the clear text chat, since they have access to the messages. So on the other end, it's not really received. But of course, as I mentioned earlier, they can't really filter secret chats. The only way would be to have like an end-to-end bypass, which I guess they don't have. So they can't really filter secret chat, and this is the actual attack vector we are going to analyze. So let's move to the fuzzing efforts and the methodology I've adopted in this research. I have a specific methodology, usually, which can be summed up either by the keep it simple, stupid title, or this specific InfoSucks meme, which basically says that I always try to do the laziest and easy test first and see what happens. And then if I really need to get smarter or try some more advanced methods, I will try them only if I really need to use them. So during the first phase, since Arlotti is open source, I just decided to go with coverage-guided fuzzing, since we can easily instrument the Arlotti code and fuzz it. So the initial corpus was collected pretty much automatically from the Telegram communities online, since when I started my research, some of the animated stickers designers were already publishing some some of them online, so I could just download them and add them to the corpus. After, by just using the default mutator, first using AFL++, then using libfuzzer, so by just trying to bit flip them or mess, for example, with integers, Arlotti crashed already, which was a really interesting point, because still to this day, I don't know if either no one fuzzed it before me or nobody reported any issue in this code. I still don't know. But since I had already some crashes, I wanted to try to have a little of test case minimization and root cause analysis. The problem here is that since the animated stickers coming from inserted in the corpus were coming from the online communities, they included a lot of useless data for the actual crash to happen, for example, metadata or comments or stuff like that, because I didn't try to minimize them, because as you can imagine, since they included this much data and they had to respect first the JSON specification, then the Lotti specification, it wasn't really simple to do. And this problem appeared again when I wanted to minimize the test cases, which unfortunately, from my experience, is just an endless brute force, because it will try to remove bytes randomly and see if it still crashes. The only problem is that I wanted the specific animated sticker to keep crashing in the same way. And since, as I mentioned earlier, I always try to find the easiest solution first and then maybe get smarter, I just decided to brute force them, but try to be a little bit smarter. So by using both half-empty and ASAN and grep. So basically, this could be like the steps you can use. Of course, manual minimization was not an option for me, actually. AST brute forcer would have required AST-aware parser and decoder, which again required quite some work. Half-empty is a tool developed by Taviso from Google Project Zero, which allows us to try to minimize a test case and test it through a script. So what I have done, I just used together address sanitizer, grep, and half-empty in order to keep that test case crashing in the same way while minimizing it. So this is pretty much what I've done. So you can see above there is the run and grep heap-based buffer overflow for white .bash script, which basically will pass the standard input coming from half-empty to the Arlotti parser instrumented with address sanitizer, and then grep the write of size 4 because I wanted that specific crash. Of course, I could have filtered for the program counter, for the stack trace, or whatever I wanted from the address sanitizer report, but I had just this specific write of 4 bytes, so I just wanted to do it this way. And below you can see the actual main command line definition, which calls half-empty, says that it must be stable, so deterministic. The 0 char is the ASCII space char because it's a JSON and the space will just be skipped. I wanted the output in the minimized JSON, and I wanted this script to run with the address sanitizer instrumented parser. we can move to just a quick view of the summary stats. Note that these are actually the very initial stats on cheap hardware. Basically, it was run on a laptop I had in our offices. As you can see, just by having it running some days, it already has found quite some crashes. Here it says locally unique, but as you can imagine, since they are both JSONs, both Lottie animations, in this case, IFL++ is not really able to categorize them and test if they are actually unique, because as we will see later, all of these crashes in the end were just 11 unique issues. Last but not least, coverage at the end of my research was around 90%, so I was pretty happy with it. So I didn't really put additional effort after the structure-aware fuzzing that we will see later. Let's have a quick look at the harness. As you can see, it's just the load from file and the render sync method call. Just a thing to note is that I added the specific frame number which the RLottie library was trying to parse to render in order to being able to spot which specific frame crashed the library. So, as I mentioned earlier, the animated stickers, so the Lottie animations, must actually respect two specifications. The first, they must be valid JSONs, and the second is that they must respect the Lottie specification. So the problem here is that the built-in mutators in the most famous fuzzers, like I mentioned earlier, I used AFL++, then libfuzzer. Of course, try to mess with some standard techniques like bit flipping, playing with the integers and other stuff. But in this specific context, since we have already all of these constraints, they are not really useful, since as we can see, this is actually a reference to a bug in V8. But in the RLottie case, -0 is really not, it's useless because there is no such type of layer. As you can see, the TY is the key for the type of the layer. So it's a wasted mutation, a wasted test case, so I didn't want this. In order to improve this, always surfing the KISS framework, I tried to search online, and Google had this technology which is called protocol buffers, or protobuf, which is a language agnostic grammar in order to define pretty much anything. As you can see in this example, on the left part, you have the message type person, which has a name, an identifier, and email attributes. And on the right part, you can see that in C++ it's really easy to parse, for example, the standard input into a specific type which was defined in protobuf. So we can easily encode and decode data using a specific grammar. How we can implement this in a fuzzer? Basically, we first, as I mentioned, we need to define a grammar. So all I've done is writing the RLottie protobuf. I chose to write the specific RLottie specification and not the Lottie animation specification, because they have some differences, since I was targeting the RLottie library and not each and every Lottie parser. As you can see, most of the attributes are primitive types, so some doubles, some unsigned ints. But the most interesting one are actually the layers and assets, because as we have seen earlier, actually the most of the juicy stuff is in the layers part. So by integrating this grammar logic in a fuzzer, we can really do some actually useful mutations. So for example, here you can see a really dumb example, but it's just to make you understand that this can be actually very powerful, translated to a target complex as Arlotti or more. Instead of trying with weird numbers, we will try only the accepted, for example, types of layers, since we really want to advance our coverage, so potentially reach 100% of coverage. So instead of using the built-in libfuzzer mutator, Google has also created the libprotobuf mutator, which is a external mutator which can be used in many fuzzers. At the time, if I remember correctly, only libfuzzer supported it. But in this way, we can easily tell the fuzzer that we want to use this mutator and we want only useful mutations, because we define the grammar and we define the logic that the grammar must respect, both in the grammar and in the harness. So thanks to this, we move to the second phase of my fuzzing methodology, which is the structure-aware fuzzing, which is basically fuzzing from a structure-aware mutator, which allows us, as I said, to make useful mutations and potentially advance the coverage we reach. So it can be pretty much summed up in these 4 points. The Arlotti proto, which is the protobuf definition of the Arlotti specification. Then, thanks to this grammar, we create an animated sticker from scratch. Then we pass this to libfuzzer in order to pass it in turn to the mutator, which will mutate it in a useful way. Then, since this is still in the protobuf format, we need a way to convert this to a JSON in order to be accepted by the parser. So this conversion logic is implemented in the harness, which will in turn actually pass the created animated sticker, created and mutated animated sticker to the actual parser, which will try to parse and render the sticker. Let's now have a little comparison of the fuzzers I wrote. Just a little disclaimer here, these benchmarks are not to be taken really like in a deterministic way, since you might get some other results. I've divided the columns into 2 main fuzzers, since as we have seen, first I tried with simple coverage guided fuzzing, then I moved to structure aware. As you can see, I had quite some coding iterations for the harness, because since in coverage guided I just needed to parse it from the file system or a string, load it in memory, parse it, and then render it, while in structure aware I had to implement all of this Arlotti grammar and protobuf to JSON conversion grammar, so I had to write the harness quite some times. But a plus of this improvement is the invalid mutations percentage, because as you can see, most of the coverage guided mutations either broke the JSON specification or weren't really useful from a Arlotti grammar standpoint. So I was pretty much wasting time and executions. Downside of this is a slowdown, of course, because since there is a lot more logic involved, it's way slower. Instead of just bit flipping, it's creating from scratch animated stickers and mutating it by respecting a specific grammar. Last two rows of this page, as you can see, the time, of course, it's really different, since with Coverage Guided, I just needed to download quite a bunch of animated stickers from Google and then run it after I wrote those 5 lines of harness. While with structure aware, I needed to, as I said, write all of this grammar and conversion logic, which took quite some time. Time to results 2 is quite different, since even if the coverage was advancing faster than the simple coverage guided fuzzing, it still took quite a lot of time in order to arrive to more than 90% of coverage. So that was another difference. Moving to this second page, as I said, in the coverage part, in the simple coverage guided, it really depends on the corpus, since I wanted to have the most diversified corpus for starting the coverage guided fuzzing, but still I couldn't really advance the coverage after a point, because the mutator didn't have the knowledge to create useful objects or layers in the animations in order to improve the coverage, which instead was possible in the structure aware part, since theoretically I had no limit, no coverage limit, because it was just a matter of time, and the mutator would create pretty much any kind of animated sticker. 2 points about the test case minimization and comparison. As I mentioned earlier, in coverage guided, simple coverage guided, it's possible really only through brute force or, of course, manually, but that was not an option. And the comparison also is low, since we actually need to minimize them, because, as you can imagine, 3 kilobytes of single line JSON files are not really simple to compare one another without a AST aware decoder and encoder. While on the structure aware, it's pretty much direct and scriptable, since we already have the grammar logic, so we can just use it in order to minimize and compare them. Last but not least, some points about the number of unique issues I have identified after root cause analysis, since as we have seen, by looking at the stats coming from the fuzzers, of course, there were thousands of crashes, but after root cause analysis, they came down to 11 and 13, but still, as you can see, I could find two additional issues by implementing this structure-aware fuzzing. So let's move to the findings I've identified, have a live demo, and some considerations about the exploit limitations of this specific attack vector. So as you can see here, in the end, I found 13 issues. This is the list of all of them. While I usually wouldn't consider null pointer dereferences as actual security bugs, in this case it was different, since as we have seen in the Android example, each and every time you open the chat crashes, since it will try to parse and render the malicious animated sticker, and in the end it will crash. So non-technical people would have quite some problem in order to retrieve the messages shared before that specific malicious sticker. Of course, this is not the case for chats from strangers, but it could be used from chats with maybe more personal chats. These are just the types of issues I have identified. You can anyway see all of them and their root cause analysis on our website. This is schilder.it/advisories. And as you can see in bold, there is the IP-based out-of-bounds right, which is what we are going to have a look at today. Oops. So let's have a quick look at the address sanitizer report for this specific issue. As you can see, we can see the type identification by address sanitizer, which is IP-based buffer overflow, and that is a variety of 4 bytes. This is the stack trace. So as we can see, the specific problem is in the generated gradient color table method, which we are going to have a look at now. So as you can see here, maybe it's a little bit small, but I will walk you through it. Our input basically arrives at the stops, v-gradient stops vector, which is the first argument. As we can see, it will influence at line 14 and 15 both the start and cur variables. Then, as you can see, on line 17, it will influence also cur color. The only constraint here is that it must respect the ARGB encoding, which is pretty much the only constraint here. We arrive at line 21, which will define the first color in the color table, which is of size. We arrive at the while loop on line 23, and we can see that actually POS is not checked to be smaller than the size, which is the size of the color table array, which means that potentially we can write out of the color table array bounds, which is exactly what happens on line 24. So let's have a live demo of this issue. Okay, it's not shown here. I should say, can you mirror the screen? Can you mirror the screen? Okay, we'll just move them there. Yeah, because okay. Nope. Oh. Sorry. Okay, it's there. Start. Yeah. Okay. Yeah. Let's try this one. Okay, it was closed now. Okay. You can see on the right part of the screen there is my device, which is here. It's just mirrored on the screen. While on the left, you can see my command line, which is from connected to a server. This is actually the proof of concept I have sent to the Telegram security team. As you can see, I can just define the pretty much recipient username and then the specific animated sticker I want to send. So let's see if this works. So as you can see on the right part, my script created a new secret chat, and it was automatically accepted by the, in this case, the victim. I don't know if you noticed it, but at the start of the demo, my Telegram contacts were shown, and there were no contacts saved in Telegram. So this polyct one is actually a stranger for this specific recipient. As you can see, the secret chat was automatically accepted, and if I will just open Logcat so we can have a look at the logs. Okay, if I click on the chat, it will actually be parsed, and the recipient client will crash. As you can see, there was a segmentation fault during the access of memory. In this specific case, it was trying to write on unmapped heap memory. So, of course, it crashed. So let's move back. Okay, now. Okay. So let's move to some exploit considerations. So as I mentioned earlier, the attack surface is only available in secret chats, since apparently clear text chats are filtered. Moreover, the Telegram APIs allow large-scale attacks from a single computer. As we have seen in the demo, I was able to just target any user I wanted through that specific script, but of course you can scale it. The specific heap out of bounds write issue we have analyzed is probably only exploitable on 32-bit platform, since it's just a write of 4 bytes. Last but not least, I couldn't find any remote info leak or memory probing oracle in order to bypass ASLR, which was the main problem, in order to create an exploit from these specific issues. I have also wrote some ideas I got after doing this research that I can share with you, which can maybe improve the results and lead to additional issues. So first, we could use the online-offline indicator as a memory probing oracle. Of course, this would require a very fast crashing or non-crashing state, which I didn't study much. Or we can craft, for example, a polymorphic animated sticker which passes the Telegram API checks for validity, making clear text chats valid vectors too, because every time you create a sticker set, the sticker you want to add to the set is actually tested in the case of animated stickers. So maybe there is a way to create a malicious animated sticker which doesn't create problem on the Telegram API sides, but creates problem on the specific client. About this specific issue, 2 ideas I got is to prove either, as I suppose, that the Telegram APIs are vulnerable to the same issues in case they use the same parser as in the clients, so the RLOT parser, or if they are using a different parser, find some parser differential issues between those 2 parsers, so find some additional issues in the differences between the 2 parsers. Last but not least, skip inside the fuzzing process the protobuf to JSON conversion, since the fuzzing process might actually be faster this way, but as I mentioned it in the slide, there could be like self-bugs, as in bugs that you actually introduce by skipping steps in the real case, so they might lead to some problems there. Another thing to mention here is that since I added the proof that the Telegram's API are vulnerable too, because at this time the Telegram's server code is closed source, so we can't really just have a look at the code like for the clients. So let's move to the closing remarks for this presentation. First, since Telegram not only fixed my memory corruptions, they also implemented some additional protections. One of these is contained in this specific code snippet, which, as you can see, it will try to check that actually the animated sticker that you have received is part of a public sticker set. So you will not be able, thanks to this code, apparently, to send custom animated stickers, because even if they were received on the recipient part, they will not be parsed and rendered, since they will check that they are actually part of a sticker pack, which allows them to keep animated stickers in the secret chats as a feature. So after this defensive depth measure, you not only need to find additional issues in the Arlotti library, but you also need to bypass this specific check, which in my opinion was introduced because in my proof of concept I faked sticker sets references, because they actually checked that once the animated sticker was received, it had the attributes of the sticker set, but they didn't actually check that they were really part of those sticker sets, and in the end they added this new code. Another option they introduced is this filter new chats from non-contacts, which is not enabled by default, so most probably most users do not have it enabled, but basically what it does is it will archive and mute new chats coming from non-contacts. So in this case, there will not be the risk of you clicking on the chat or the malicious sticker automatically being parsed and rendered, because they will be non-available directly in the user interface. Some specific details of the patched releases. As you can see, they are just the official clients, and the Windows one, for example, is missing, since because of the need of a secret chat environment, the Windows client at the time didn't support secret chat, so I didn't even test it, because as I mentioned earlier, apparently they are filtering clear text chats, so it's not really vulnerable, as in you can't exploit it. Probably the library is vulnerable, but you can't really reach it. Last point, that is pretty much a really long-standing debate between the user experience and the security defaults. My personal experience with this research is that Telegram really cares about user experience and not really much about security, because as we have seen, there are some protection that were included only after some issues, or they introduced some features, for example, the animated stickers, without really much testing, or in this case, fuzzing. So thank you for listening to my talk. I will be available for some questions now. In any case, you can find me on Twitter at @polict_, and you can keep up with our researches at shielder.it. Thank you.